Okay, next up is Dr. Michael Hecht. He is at NASA JPL. He's the principal investigator on the MOXIE mission, and he's going to give us a project update.
Happy to be here. Very happy to be here. A lot has happened since I was here last year. So I heard Jim kindly deferred a question about MOXIE to now. I hope I answer it, or happy to do it in the Q&A. But the big news is like everybody else on Perseverance, we are now on Mars and operating, and that's very exciting. So I'll just try to give you the briefest of summaries, because again, I talked to you guys last year, probably many people heard it, but here's what we're doing. When we send people to Mars, this is the last audience I have to tell this, the straightforward mission, the Holman transfer mission, as laid out in the design reference architecture, is one where you take advantage of the natural orbits of the planets. You leave, you take 6 months to get there, and then a year and a half later, 539 days by this diagram, the idea is to take advantage of the natural orbits and send a cargo mission followed by a human mission. That's the other key aspect. So the way these orbits work, that means that when you send your cargo mission to get ready for human exploration, you take about half a year to get the stuff to Mars, and you have about a year and a half to wait before the human crew launches from Earth. And you do a few things with that, okay? Of course, you put in place the key elements of the human base, the habitat, the rovers, critically a 25 to 30 kilowatt power plant, assuming about a crew of 4, and an ascent vehicle that will allow that crew to come home, a fully fueled, and by fuel I mean both fuel and oxidizer, ascent vehicle. The single biggest thing in that whole package is the propellant, and by far the propellant is dominated by oxygen or oxidizer. So that's about 25 tons worth of stuff. The whole point of this venture is to not have to bring that 25 metric tons of oxygen to Mars when we send our first crews to Mars, and also to take advantage of the fact that if we pre-deploy all this stuff, we've got a 25 to 30 kilowatt power plant that will eventually support the human base, but is doing nothing. Okay, so the idea would be to use that to produce at least oxygen, if not the full propellant package, until the human crew is ready to head for Mars. Okay, so MOXIE, that's what MOXIE is for. It's a small scale model because we do not have a 25 to 30 kilowatt power plant on Mars right now. We have what we want, but frankly, the scale up in size is not the biggest challenge. There are other bigger challenges. So being able to test the basic technology and show that end to end, we can make this work in situ on Mars without anyone turning the knobs, is a huge accomplishment, and kudos to NASA for recognizing this and investing in doing it today so that we can go to Mars tomorrow. So what does it do? MOXIE makes 6 to 10 grams per hour out of thin air, as I like to say, because the air is thin, about 1% as thick as Earth, and it is made almost entirely out of CO2, which actually means there's 20 times more CO2 in the Mars atmosphere than in Earth's, even though it is so thin. So what all these numbers mean in reality is if we run for an hour, we'll make enough oxygen for you to breathe for 20 minutes or so. And we're kind of like a smallish, a medium-sized tree. Not that MOXIE works like a tree, but like a tree, they both take in CO2 and they both put out oxygen. Which certainly helps us live on Earth, and we expect will help us live on Mars. So I think Katie already showed this. We're sitting down in the belly of the rover with no windows. So while we are fascinated and thrilled to be part of this wonderful exploration of Jezero, it kind of doesn't matter where we are in terms of MOXIE operating. Very, very briefly, again, this has been done before. Just pointing out, we start with Mars atmosphere, and which has 5 to 10 millibar of CO2, depending on time of day and depending on season. We collect it, we compress it. We probably over compress it in hindsight. We put more energy into compression than is really needed. We could run at much lower pressures and will in the future. But we feed this feedstock, the CO2 feedstock, into a solid oxide electrolysis system that runs at 800 degrees C in a highly insulated package. That separates some, not all, a fraction of the CO2 molecules taken into CO and O, and very efficiently separates those two streams. And in one little wrinkle is that we then, if you look at the bottom diagram, we then return part of the tail gas to the front, to the compressor, to make sure we have enough CO in that intake gas to make a reducing environment so we won't oxidize the cathode. And that's a subtlety, but I'll come back to it in a minute. So to get the levels of oxygen production we do, it's not enough to have one cell. We stack up 10 of them in series, electrically in series, so they're all producing oxygen, and that's how we get up to the 6 to 10 grams per hour. They're separated by these formed, centered, so-called interconnects, and those have all the patterned flow fields within them that direct the CO2 and the oxygen coming in the proper directions from these tubes you see at the bottom right. So this is great to have this little stack. And how do we go from this little tiny thing, this big, to an instrument this big? Well, to begin with, we have to package it. JPL did a nice job of this. But first thing they had to do was to heat it up in an oven to 800 C. And so they built kind of a makeshift oven where the heaters are in the end caps that partially surround it. Then they had to hold it still, but they also had to insulate it so we wouldn't lose all that heat. And those are kind of two competing requirements, but they ended up with a system with a very structurally solid insulation called Min-K and heavy springs, and then fill in the rest with aerogel. So when you're all done, you have the little number one, which is the stack, number two, which is the stack assembly or package, number three is the compressor, and number four is just the very beginning of the assembly process. Okay, and just one other, I don't want to get into technical details, but one other wrinkle I'd like to note is that this is challenging, and we can break MOXIE if we don't run it right from the ground. And the key issue is that what you have on the x-axis here is the fraction of CO2 we're converting to oxygen. And what you have on those red and green and blue lines, depending on our operating temperature, the solid lines tell us the maximum voltage we can go to before we start depositing carbon on our electrodes. You can see what that looks like in the upper left. It's not nice, and it's end of game as far as operating on Mars is concerned. If we go too low, below the dotted lines, we don't make oxygen at all, and in fact, we can oxidize our cathode. So we must stay in that safe zone. That thing that looks like a TIE fighter there is our uncertainties, an estimate of our uncertainties. And obviously, the farther we go to the right, the more oxygen we try to make from a higher percentage we try to convert to oxygen, the tougher this gets. So I'm just defining some of the challenges. And I talked about all that last year. And when we last spoke, ended with this, here is MOXIE getting put in the rover, and this note saying Perseverance launched was a year ago and will land on February 18th, 2021, which is obviously 6 months in the past, 8 months in the past. Boy, time flies. Okay, so the rest of this talk, I want to talk about what's happened since then. So first of all, how do we do a run? Well, we have a lot of little knobs, but the big knobs we have to turn are the temperature, this 800 degrees C plus or minus that we run, the speed of the compressor, how much gas we collect, and the current voltage relationship of this electrolysis cell. We typically control the current, but we actually would like in the future to control the voltage and let the current follow along. Now, as you can see here, let me go back to that slide. We spent 2.5 hours just heating the thing up, and which leaves us about an hour's worth of power left to actually do stuff, to actually make oxygen. And the way we plan that is we break that hour into segments that have different functions. So there's a reference segment that we always run so we can compare one run to another, no matter what else we're doing. And then the second and third segments that you see here can be doing any kind of experiment we have in mind. And then at the end, we do want to reset to the starting conditions just to make sure nothing changed while we were running. And so what do we do on Mars? Well, we get a MOXIE sol every month or two. It's been a month up until now, more or less. And as I mentioned, we take pretty much all the spacecraft power for the day that's available to the payloads. That's about 650 watt hours. This also takes power to run the rover. And we spend most of that heating up and about an hour running. But we want to operate in all seasons and times of day. Similar issues to what you heard about on Ingenuity, where it's not just the lift that changes, but the density of the air affects MOXIE, as does the temperature. And then we have a lot of targeted experiments to understand some of the properties of MOXIE. But overall, we also want to see just how it ages over time. Okay, so just to highlight the atmospheric density issues, the daily maximum to minimum is a significant difference. The seasonal variations are even more significant. And so if you go to the top of that maximum nighttime, the top line is nighttime curve, to the bottom of that midday curve, that's almost a factor of 2 in density. If the air is twice as dense, we take in twice as much feedstock into MOXIE, so it's a big issue. So we plan to run in all these solid circles, and if we can, we plan to run in some of the dotted circles if it works into the mission timeline. And maybe for us, we'll be lucky and get a dust storm. For other instruments, maybe not so much excitement, maybe for Meta. So what have we done so far? We did a number of checkout runs, as we do often in between the main runs, where we don't actually make oxygen, we don't even necessarily heat up. But the first production of oxygen was April 20th, the night of Sol 59, the morning of Sol 60. And we made over 5 grams of oxygen, which will keep you alive for 10 minutes, with a peak production rate of 6 grams per hour. We ran for the second time on May 12th. This was more ambitious. We produced 7 grams of oxygen with an 8 gram per hour peak. So that was 1/3 more. And for the first time, we ran the SuperCam microphone so we could listen to our compressor, which is a key diagnostic. And it took some doing to run the 2 instruments at once and synchronize them. And then on Sol 100, we said we're going to go to a lower density time of day and a warmer time of day. And we ran midday on that one, and we still got 8 grams per hour. And we started to do some experiments about how to nail down the purity of the oxygen. Then we ran again on Sol 155 at nighttime with the microphone. And this one, we did a very clever experiment to distinguish the resistance, the electrical resistance across the stack from other electrical resistances in series, such as over the wires and over the contacts. And that's critically important for us. And our 5th run was just recently on August 17th, where we did another targeted experiment to help determine the purity. So those were our 5 oxygen runs. And I wish I had like a great video to show you a cloud of oxygen coming out of MOXIE, but you can't see oxygen, so I can't do that. So basically, this is what it looks like if we say how much oxygen have we made as the time goes along. We warm up for 150 minutes and cumulatively it goes up a ramp. The reason for the wiggle is we kind of pause to do something else as part of that sequence. And that's what it looks like, 623 watt hours. We acquired current voltage relationship curves, and we found the best time to do this is not by taking a nice step and waiting and taking a nice step and waiting, but watch what's happening while it's doing that nice step. And it goes through all of these current voltage points. And we got very, very nice current voltage relationships, which is key to understanding an electrolysis cell. We looked at robustness, and the most brutal thing we can do to these stacks is to heat them up to 800 degrees centigrade and then cool them down again, and then heat them up again. And something you really wouldn't do if you had an operating system. And so we keep track of how much the cell resistance changes from run to run. We have some experience with an engineering model at the top. showing it's fairly large. And the flight model we sent, we really thought we had this nailed, and we did. That while you see some increases, they're very, very tiny. We could do 100 runs like this and still be able to meet all our requirements afterwards, assuming that this slow rate of increase continues. And just to be clear, what we're measuring here, the bottom, the x-axis is showing operational cycles. The first one on Mars was number 9, 10, 11, 12, and 13, with a 5 on Mars. The previous ones were on Earth. And this IASR is the resistance I was measuring. The full acronym is intrinsic area specific resistance. So we are able to track our robustness and our cycle-to-cycle degradation. We have some preliminary numbers on purity, and basically, as long as we keep overpressure on the oxygen side, the anode, we can't measure any impurity. If we intentionally put an overpressure on the carbon dioxide side to see if we can force any CO2 into the oxygen stream, yeah, we can force a little bit in, enough to measure, but over any plausible range of operation, up to a 15% overpressure on that side, we get it's bigger than 15%. It's 0.15 out of about half a bar, so maybe 30%. We still meet our 98% purity requirement. So there we go. That works. We did some focused experiments. I mentioned, for example, where you step the temperature from 780, or in this case 790, to 800 to 805, and measure the voltage, and that tells us something about the series resistance that I mentioned. And this very cool experiment, I won't try to play any microphone recordings, but I'm showing you a spectrogram, which is to show the frequency spectrum. In each vertical line is a time slice. And you can see that the points at which we change the compressor frequency, this whole pattern of dark lines, which are the frequencies we're exciting, changes. And we can measure with this microphone up to 20 harmonics of the speed at which the compressor motor is turning, and see them change. In fact, this turns out to be a more accurate way to measure the compressor speed than the thing that's supposed to measure the compressor speed. So we're really happy with this diagnostic. And if anything should go wrong in the future, this will really help us debug what's happening. So thanks to the SuperCam team. And I'm going to conclude, because I would like time for questions. I have a few slides with a couple of conclusions, but just, we're not ignoring going to this full-scale system. Our partners at Oxyon Energy out in Salt Lake City have already developed the stack on the lower, you see pictures of on the right. The top is a conceptual drawing. The bottom is the real thing that will produce on the order of 1 kilogram per hour, and a few of those will get our 2 to 3 kilograms an hour target that we'll need for the next gen system if we have our power system. Air Squared, which is the company that developed the compressor, is working on a scaled up version of the compressor. At MIT, we're looking at what is also a big, mass and volume contribution to that system, which is the filters. We're looking how to make those smaller and lighter. We're also working with a local company, BlazeTech, in helping them test their electrostatic dust separator. So we know enough about this full-scale system now to know that it will weigh about a ton. It will use about 25 kilowatts of power, and over the course of a year, will produce 25 tons or more of oxygen, which is sufficient to get the crew of 4 off the planet and on their way home. So lesson learned. Well, what was stunning about this is we couldn't distinguish operation on Mars from operation in the lab, which is really what we hoped for. And that said, so it's working fantastically. I'm trying to remember the word Jim Green used, but I heartily agree with him. It's sensational, I think he said. That said, it's a complex system. The devil's in the details, and we work very, very hard to make sure we get those details right. And sometimes we need to be extraordinarily clever to do things on Mars that we could do in half an hour in the lab. But that's the nature of working remotely. And finally, the path to the full-scale system is clear, if not without challenges. And I note in particular, making it produce 200 times more oxygen is the easy part. It needs to be smarter. It needs to be more robust, and it needs to be able to operate continuously for over a year. Those are likely to be the hard parts. So with that, I mean, I can't even begin to write down all the people who contributed to this. This gives you an idea of the people active in this phase. Dozens more at JPL and the development team I didn't list, as well as the staff at our key contractors, Oxion and Air Squared. Pandemic. Well, this was our last in-person science team meeting in November 2016, and not everybody can travel, so this is a group of about 20 something here. And I'm happy to report that we got back together again last week in Copenhagen, and there were only 10 of us. The rest of us were on Zoom, but it really felt like we're back in business again as a team. And as you can see, comparing the two pictures, we're still eating and drinking and enjoying ourselves. So with that, thanks to all the partners, thanks in particular to NASA for getting 3 directorates together: Human Exploration Directorate, the Space Technology Directorate, and the Science Directorate, to make this one enabling experiment possible, and to take a giant step toward sending, who knows, maybe my grandchildren to Mars. Thanks very much. Happy to field questions.
Thanks, Michael. Handing over to Lara for Q&A.
You bet.
All right. Hi, Michael. My name's Lara. Can I ask a couple
Lara.
of questions on behalf of the audience? And the first question we got is from Carol Stoker, and they're asking a really great question about not so much about Mars, but about going back to Earth and the Earth. And the question is, can a MOXIE-like system be used to do direct air capture of CO2 on Earth to fight climate change?
Thanks, Carol. I would say no. I'm sorry to say no. It's a very common question we get asked quite a bit. There are better ways to do carbon capture. We're not particularly good about that. Where MOXIE might come in, it might, is once you've captured carbon dioxide from the air, you need to do something with it. And part of the reason I say we're not good at carbon capture is what we do to it is really energy intensive. We tear apart the CO2 molecules and turn it into oxygen, and then we still have to do something with the CO. Otherwise it will just turn right back into CO2. So that would take even more energy. So it is one way to convert that captured CO2 into something that we can use, like more oxygen. But I suspect it's not the most efficient way because it does involve tearing molecules apart. And I think biological systems, probably from a system perspective, are a more effective way to mitigate, to deal with carbon, with recycling CO2 and back into something useful. Thanks for the question.
Thank you. Well, the next question is, what other gases would MOXIE be able to produce with a few changes?
Well, of course, one thing to remember, or just to make clear, I should make clear, is MOXIE is essentially a fuel cell, okay? And fuel cells can run in either direction, just depending on whether you put positive voltage or negative voltage. So the fuel cell reaction for MOXIE would be, you put in carbon monoxide and oxygen as your fuel and oxidizer, you get out oxygen, you get out CO2, you get out electricity. And I'm saying that because kind of anything you can do with a fuel cell, you can run backwards. The big one on Mars would be to do electrolysis of water at the same time. And typically you do that in the same system. You do co-electrolysis. So you put in water and CO2, kind of like, now it's kind of more like a tree. And a tree will do that and get carbohydrates out. What we get out would be a fuel, or maybe methane, or maybe paraffin and oxygen by running those two together. And there are other technologies for doing water electrolysis, but this is a very competitive one that is being pursued. The only gas in substantial quantity around on Mars is CO2, and then you can find water. So while there are many more things you could do with this technology, I think those are the two big ones.
Thank you for the answer. And the next question is, do you know if SpaceX is planning to include MOXIE into the Starship design?
Hey, if you can find out, please tell me. Okay, I'd love to know. They've talked about it. It's not my understanding that they have done much more than thought about it at a system level and how it fits into their system design, and that's critical. But I don't think there's been any real technology development, but I honestly don't have the insight to know.
All right. Next question. Will future iterations of MOXIE have a technology demonstrator to make fuel in Mars?
In other words, will we do this again with the next generation? I can't speak for NASA. Maybe that's a question should toss back to Jim Green. But I'll tell you, my opinion is that I doubt it, only because there are so many technologies. We ought to be testing on Mars before we trust our astronauts' lives to them. And I think MOXIE the MOXIE technology has had its turn. And next time we do this, something else will rise to the top as being the key one to demonstrate. That may be the liquefaction of the oxygen, and trying to demonstrate a long-lived oxygen no loss storage system, for example.
Thank you. And I guess we have time for one more question. And
Great.
This is a question from Amit, and they ask, can compression provide some heating? And can a future design have a solar oven?
Wait, I'm sorry, can compression provide heating? And what was the second
Heating.
part?
And can a future design have a solar oven?
Oh, a smaller oven? No, we actually don't want a smaller oven. We want a bigger oven.
Not a smaller, but a solar.
A
solar oven.
I'm not. Oh, solar.
Yeah, solar.
Oh, I'm so sorry. Well, the oven is not the main consumer of power. Well, right now it's the compressor, but in a future system, that would be the actual electrochemical energy we need to provide, and we need 25 to 30 kilowatts. So, for sure, you can do 25 to 30 kilowatts with solar and batteries. I don't believe that's the way NASA's going, and it looks like the directions for at least the US, the NASA space system, will look to nuclear and not to solar to provide that power system for the human mission. But again, I defer to NASA for the definitive answer to that.
Thanks, Michael. We are out of time, but really, thank you very much for the important work you're doing with MOXIE. Can't be understated at all.
Thank you so much for
Perfectly
the
understandable.
opportunity.
Thank you for being with us.